In the previous part of this lecture, we discussed about hypothesis testing of one sample provided we do not know the population standard deviation, and in that case, we were using the t-statistics or the t-value. We had, just like with the case where we know the population standard deviation, there is actually two approach. And we have already discussed the first approach, which is the p-value approach, where we are going to find the value of the p, the area beneath the curve, from the value of this the area beneath the curve that is defined by the boundary of our sample mean. Now, the other approach is the critical value approach, and this is what we will be discussing in this part of the lecture. So I'm going to reiterate the previous example that we used when we did hypothesis testing when in the p-value approach. So this one, similar question, but the approach now is on the critical value approach. So just to recap, the problem is that a psychologist claims that the mean age at which children start working is 12.5 months. Now, Carol wanted to check if this claim is true. She took a random sample of 18 children and found that the mean age at which these children started walking was 12.9 months, with a standard deviation of 0.80 months. Using the 1% significance level, can you conclude that the mean age at which all children start walking is different from 12.5 months? Assume that the ages at which all children start working have an approximately normal distribution. Now let's look at our problem. So the claim was that the population mean of the age at which children start working, this is our population mean, it's the claim, is 12.5. And now our sample is relatively small. So we have 18 children in our sample. The sample mean is 12.9. The issue here is 12.9 different using this sample statistic or sample mean. Is it as different from the population claim that it's really 12.5? So this is a difference of 0.4 months, really significant, because this is our sample mean. And then this is our sample standard deviation, so 0.80. We do not know the population standard deviation, but we know the sample standard deviation from our sample is 0.80. So our significance level is 1% or alpha is 0.01. And the question is it different from 12.5? So we can now state our null and alternative hypothesis. So the null hypothesis that our mean is really 12.5. So 12.9, based on our sample, the difference of 0.4 is really very small. It's not significantly different. Therefore, 12.9 is close enough to 12.5. What it means is that 12.9 months is close enough to 12.5 months that the population mean is actually 12.5 months. So that's actually the claim. And that is what our null hypothesis is telling us. So even though we have a difference of 0.4 months, the sample mean is greater by 0.4 months from the claim of the population, that difference is negligible such that we can still say that even though our sample population is our sample mean is 12.9, it's close enough to the claim of 12.5. Therefore, our population mean is still 12.5 because the difference of 0.4 months is really insignificant. And that's actually statistics. We must hypothesis testing at the very core, we just want to know if the difference is significant or not. Now here, the null hypothesis, there is no significant difference. And then we have our alternative hypothesis, which is, the difference of 0.4 is actually small. That's why, even though the claim is 12.5, but from our sample, it's really not 12.5 because we found 12.9. There's a difference of 0.4 and it is a significant difference. It's not that small that we can say that the population mean can still be approximated at 12.5. So that's our alternative hypothesis. And here we have a not equal to sign. And then step 2, we are going to determine the type of test or our distribution. So we have a small sample size and of less than 30 because we only have 18 samples. But they said that the population is normally distributed and we do not know the population standard deviation. Therefore, we can use here t-distribution. Then, for critical value approach, here is the difference between the p-value and the critical value. In the p-value, we are going to find the area of the p. But in the critical value approach, we are, instead of finding the area of the p-value, or rather the p-value, we are going to find the area defined by our alpha, or our significance level. So, the not equal to sign is means that we have a two-tailed test. So therefore, our rejection region lies in both tails. So since it's two-tailed test, our alpha will be divided into two because the total rejection regions, the area of the rejection region is our alpha. So since it's two tails, it's divided into in both tails. So we just divide it by 2. So 0.1 divided 2 is 0.005. Here we are going to find the critical value of t. What is the critical value of t? It's actually the value of t from that divides the regions or the rejection region and the non-rejection region. And we're going to find it through the t-table. So if you look at your t-table, we have your area of 0.005 and then against your degrees of freedom, which is n minus 1. So n is 18, so minus 1, that's 17. So according to the table, I'm no longer going to show it to you. But it's actually available at the end of the book that we have. Anyway, the critical t-value for a degree of freedom of 17 and an area of 0.005 is, this is in both tails. So you have negative 2.898 and positive 2.898. So to illustrate that, here is our t distribution. And our t distribution, since it's two-tailed, our alpha is divided into both tails. And we have here, this is the rejection region, and our critical value defines the line that divides the the rejection region and the non-rejection region. So since it's two-tailed, we have two points here, negative 2.898 and positive 2.898. And this is our alpha. So if our t value, the sample means t value falls in the rejection region, we are going to reject the null hypothesis. But it falls here, we are not going to reject the null hypothesis. So in the critical value approach, we will have two values of t. One is the critical value that divides the rejection and the non-rejection region. And the other t-value here is our test statistic. Our test statistic is obtained from the value of our sample mean. So sample mean minus the claim, the population mean claim, which is 12.5, divide the normalized normalized sample standard deviation, which is the standard deviation divided by the square root of the number of samples n. So we have 0.188. So just plug it in the equation, we get a value of t. So this is our test statistic, 2.121. Now, where does it lie in our region? So 2.121 is somewhere around here. So it's in the do not reject area. So we can say that it's in the non-rejection region. Therefore, we will not reject our null hypothesis. So we can still say that the difference of the hypothesized population mean and the sample mean is so small that they may have occurred because of our sampling errors. And therefore, basically the 0.4 difference is insignificant, and we can still say that the population mean is still 12.5 months. So that's our hypothesis testing for the critical value approach. Now, let's have another example. So, the management at Massachusetts Savings Banks is always concerned about the quality of service provided to its customers. With the old computer system, a teller at this bank could serve an average 22 customers per hour. The management noticed that with this service rate, the waiting time for customers was too long. Recently, the management of the bank installed a new computer system in the bank, expecting that it would increase the service rate and consequently make the customers happier by reducing the waiting time. So to check if the new computer system is more efficient than the old system, the management of the bank took a random sample of 70 hours. So we have n is equal to 70 and found that during these hours, the mean number of customers served by tellers was 27 per hour with a standard deviation of 2.5. So at 1% significance level, would you conclude that the new computer system is more efficient than the old computer system? So here we are going to test whether to be honest, this can actually be a two sample No, still a single sample mean because we do not sample the old computer system. But we know that the old computer system has an average of 22 customers per hour, and the new computer system is 27 customers per hour. What we want to know is that is the difference of 5 here, 22 5 customers, that is 22 versus 27. Is that a significant difference such that we can say that the new computer system is more efficient than the old computer system? So that's the gist of the problem. So we can now state our null and alternative hypothesis. So the null hypothesis that there is no significant difference between the old and the new computer system. Therefore, the population mean for the new computer system is still 22 even though our sample mean is 27. So basically that's that. The population mean is still 22 even though our sample is 27, and that might be due to just sampling error. And then we have the alternative hypothesis, and since we want to know if it's faster, we had to have a one-tailed test because we want to know if the population mean is really faster, significantly faster than the 22 hours of the old computer system. So mu is greater than 22. So the population standard deviation sigma is not known and the sample size is large. We have 70 hours, 70 sampled hours. And consequently, we can use the t-distribution to perform this test. So the third step is, of course, finding the critical value, which is based on our significance level. So our significance level is 0.01. And since this is a one-tailed test, because we have an alternative hypothesis of a greater than sign, so we have only one, the rejection region lies on only one side of the distribution, which is on the right tail this time. So it's greater than, it's in the right tail. So we won't have to divide it. So the whole rejection region is concentrated on the right side. Therefore, we are just going to find the area, which is 0.01, and with a degree of freedom of 69. So the critical value, based on our table for 69 degrees of freedom and 0.01 area, is 2.382. So to illustrate that, it's a one-tailed test. This is our t-distribution. The critical value, again, separates the rejection and the non-rejection region. And again, this is defined by our alpha, or our significance level. And this is our rejection region. So if our test statistic, our test statistic from the sample mean falls in this rejection region, we are going to reject the null hypothesis. But if it falls in this non-rejection region, we are not going to reject the null hypothesis. So let's find our test statistic. So our test statistic is again found from our sample mean. The sample mean is 27, and find the difference with the population mean, which is the claim, which is that is 22, and our normalized sample standard deviation, and that is 16.733. So where is 16.733? It is farther along here, far right into the rejection region. So our test statistic is greater than our value of t because it falls here in this rejection region. Therefore, we can reject the null hypothesis. We can say that the difference between the rate of efficiency of the old computer system and the new computer system is significant. So the 5 customers difference is really a significant difference, a great improvement on the old system. And so that is our conclusion. So we reject the null hypothesis. We can say that and accept our alternative, which is the population, the new computer system is faster, significantly faster than the old system. So that's the critical value approach. So for visual people, or people that tend to understand things more visually, the critical value approach in either the t-distribution or the normal distribution are much preferred. But for others, they tend to use the p-value approach. Again, it's up to you which one would you prefer. But usually, culturally speaking, for us here in the Philippines, we have the critical value approach. That is the de facto thing that was being taught, especially during the high school years, because we can actually visualize if it's in the rejection or the non-rejection region. Whereas the p-value approach, it's not that much visual, but the thing about the p-value approach is that we can change the alpha the significance level without really recalculating everything. Because in the critical value approach, if we change the alpha, for example, to 0.05 or 0.005, we have to recalculate a new critical value. So we have to find a new critical value and adjust this whole curve. So that's the issue. Whereas when we just use the p-value approach, we can just compare the p-value and the alpha value. And we can now get our conclusion from that, whether to reject or not reject our null hypothesis. So that is the difference of the critical value and the p-value approach. Some people, especially for those experts now, have been at this at statistics for years, they tend to use the p-value because it's much faster. But it's really it takes a while getting used to. The critical value is good for beginners, usually, in my opinion. Anyway, so how about the testing if the sample size is too large? What if in our table, of course, we have a very, very large population, for example, thousands in the sample. So, sorry, not population, in thousands in the sample. How are we going to calculate the t since there's a limit to the value of t in our table? So if it's too large, we can use the last row, which is signified by infinity, or we can just use the normal distribution to approximate the t distribution because, as stated before, the t distribution as the number of sample sizes becomes larger, or rather approaches infinity or becomes very, very large. So our t distribution approximates the normal. It becomes very, very close in shape to the normal distribution curve. So therefore, at very, very large sample sizes, we are saying hundreds or thousands, we can say that we can just use the normal distribution instead. Okay, so that's it for hypothesis testing of sample means to approximate or to draw conclusions about our population means. Okay, so in the next part, we will talk about hypothesis testing on population proportions.